Just make sure that everybody can hear me. If you can't, maybe raise your hand or send me a little note. So some housekeeping for this presentation. It's Acoustics 101. Thank you for joining, everyone. If you cannot hear me, please raise your hand. I do see one hand here. There are some sounds played in this presentation, so be prepared for that. And I'll try to keep the volume. You may need to adjust the volume. By default, all listeners have been muted, so please ask questions on the Q&A board, and we'll address the questions at the end of the presentation. So who am I? My name is Ian Bonsma. I work for HTC Engineering. I've been doing this for about 15 plus years. I'm a senior associate in our Western region office in Calgary, Alberta. I'm registered as a professional engineer in Ontario, Alberta, and Saskatchewan. I have experience in almost all acoustics, building acoustics, so in condos, commercial office spaces, churches, community halls, environmental noise related to wind and solar projects, industrial facilities, oil and gas facilities, road traffic assessments from highways, and just other sort of arterial roads, airports, and many other sort of environmental noise, so outdoor noise related things, as well as experience in structural vibration, so walking excitation in sensitive buildings, so in hospitals, research laboratories, and then also vibration from railways and subway lines where they're building condos or office buildings very close to them. So why do we care about noise? Well, there's a couple legal requirements why we care about noise. So outdoors, there's typically environmental legal requirements, so avoiding adverse impact, so disturbing your neighbors, annoying residents or neighbors. A loss of enjoyment of property is often a term that's referred to in a lot of sort of outdoor legal requirements, and interference with sleep as well. The environmental noise limits throughout the world vary quite widely by jurisdiction. Workplace noise, on the other hand, your legal requirements for work where you're in your workplace, that's there to avoid risk of hearing loss, and that is generally 85 dBA over an 8-hour work shift. Then we also have, it's not a legal requirement, but we have indoors, and why do we care about it indoors? So communicating, comfort and productivity, avoiding fatigue. The open office environment is introduces lots of challenges for these things, and we'll get into some of that actually in a later webinar in a couple weeks. So a bit about the science of sound. So sound is air pressure fluctuations, and it's in the range of 20 to 20,000 per second. You can see, for instance, or take this example of somebody striking a drum. So we're going to get some compressions in sound waves, and they travel out as waves and propagate spherically from that sort of impact point. So in terms of sound pressure level, how do we measure this, or how do we quantify the pressure fluctuations? We have a sound pressure level, LP, and it's essentially the envelope, the outside envelope of those fluctuations. So in this case, this higher band, and in fact, it includes the lower band as well. So sound pressure level, we use the units of decibels. That's typically the degree of loudness. So much like meters or feet are units for distance. Our audible range of loudness is immense. It's more than a factor of 1 million. So it goes from about 20 micropascals to more than 20 million micropascals. So we use a logarithmic scale in units of decibels to help us, easily sort of interpret and write down, what those values, what sound levels are and what they mean to us. So sound pressure level, for those that like equations, LP is in decibels, is defined as LP equals 10 times log of, our measured, pressure over a reference pressure. So the reference pressure is 20 micropascals, which is equivalent to 0 dB, which is essentially the threshold of hearing. I don't think there's any places in the world where you can measure down to 0, but there's certainly some very quiet locations where you can get down into the 10 dB range. So we use a logarithmic scale to reflect our human perception of hearing. If we measured on a linear scale, it'd be very difficult to represent, louder sounds compared to quieter sounds. So we use a logarithmic scale. And you may have seen some of these similar graphs due to the COVID-19 pandemic and some of the numbers that are coming out from them. So decibel scale, here's a nice figure on the right-hand side that shows, a comparison of different sounds, they're all shown or indicated in decibels. So a quiet house, silent library is about 30 dBA, that's quite faint. Normal conversation at about a meter is about 60 to 65 dBA. The old gas lawnmowers, about 90 dBA. A rock concert or a jet engine, 120 dBA, and then we get gunshots or firecrackers about 140 dBA. So a gunshot is 100 billion times more powerful than a quiet house. And so this is why we use a log scale, because it would be quite difficult to compare sounds, a rock concert at 120 dB. It'd be difficult to say, well, that's 20 million micropascals. So we're going to get a little bit into decibel math. So 2 plus 2 dBA equals 5. So two sounds, each of 50 dBA, do not sum to 100, but they sum to 53. And so when you're doing addition or subtraction, we use logarithmic addition and not arithmetic addition. So one common notation that we use is 2 plus symbols, which implies decibel addition. So when we have two sound levels, we have 50 dB and 40 dB. When we add them together using logarithmic, we get 50 dB. So when adding two values, dB values, where one value is more than 10 dB than the other, the lesser sound effectively does not increase the total. So if we look over at the table on the right-hand side here, we can see if they're both the same. So if they were both 50, we would add 3 to it. So we'd get 53. But where we're 10 different, so 50 and 40, we actually get 0.4 addition. So we get 50.4. So in terms of sound, we also represent sound over frequencies. So, in addition to the difference in loudness, so either very quiet sounds or very loud sounds, our ears can also detect different frequencies, so tones and pitches. So frequency is the rate of pressure oscillation. So how quickly is that pressure changing over time? So we measure it in hertz. Hertz is cycles per second. So typically, thunder during a thunderstorm, about 100 hertz, very low frequency. Or crickets, insects that you hear out in nature, 3,000, 4,000 hertz, they tend to be higher frequency. So lower frequency, we have these longer wavelengths. So I have a bit of an example here of a tuba playing. And then we have a higher frequency sound like a piccolo. And so with those frequencies, in reality, we have a whole mixture of multiple frequencies when we're, out in the world. And so if we go to, an orchestra or a symphony, we get multiple frequencies. They tend to be on a rhythmic sort of pattern, and it's fairly soothing and quite enjoyable. And we can have noise, which, maybe construction sites, or, you're out near the airport and there's lots of people, in the concourse and planes flying and trains coming in. So it's a whole mixture of frequencies, with random spikes and peaks, and it's not really that soothing, and typically, it can be annoying, particularly when it's at elevated levels or when the background sound is quite quiet. So we measure sound, frequencies in octave bands. This is a good representation for human hearing, and it helps us to identify low and high frequencies. So octave frequency bands can be kind of inconvenient. So we say a spectrum of levels, and a spectrum does not intuitively describe how loud the sound is. So to make it simpler and more intuitive, we use an A-weighted sum, so a single number, particularly for outdoor environmental noise, so dBA. So our human ear is not equally sensitive to sounds or components of sound having different frequencies. So equivalent energy at low frequencies versus high frequencies. Our human ears are adapted over time for us to better be able to hear human speech, which is generally in mid-frequency bands, so 500 to 1,000 hertz. The frequency response of our human ear is generally referred to as an A curve, and we apply that A curve weightings to the levels at each frequency and sum the results into a single number. So I have a graph here on the right-hand side, which shows what the corrections would be to a dB, an unweighted sound level, and when we're trying to calculate what the dBA sound level is. So we apply a filter based on how human ears hear the frequencies, and this filter is then used as an overall sound level. So when I was referring to the thunder earlier down at 100 hertz, we would correct the unweighted sound level by about 20 dB down in order to sort of represent what our human ears hear. So an A-weighted sum is a good single number descriptor of the loudness of a sound. Levels are measured in dBA, and they correlate well with the potential of a sound to cause disturbance or annoyance in a community or risk of hearing damage. So many jurisdictions, utilize a dBA value for noise limits, 45 or 50 dBA for outdoor environmental noise. Workplace noise is often 85 or 90 dBA. And then this is usually referenced to some time frame, 1 hour or a 24-hour measurement. So speaking of that, we have, sound is generally not constant. So how do we represent, fluctuating or varying sounds over time? So we have, a couple sounds here. We have a steady sound. It's relatively straightforward to, figure out what the sound pressure level is, the LP or the dBA sound level of this. But if we have a sound level that's fluctuating up and down, how do we represent that as a number that we can understand? So a common descriptor that lots of people use is LEQ, so energy equivalent sound exposure level, and it's generally measured over a given time period, often 1 hour or 10 minutes. It's like an average, but it's a logarithmic average. So for definition, it's the hypothetical steady sound level that would contain the same energy in a given period of time as the actual time varying sound. So in the graph on the right-hand side, an arithmetic average might be a step or two lower, where the LEQ average, which is the energy average, tends to weight the higher energy, the peaks, a little bit more. So LEQ correlates well with the potential for sound to disturb residents, correlates well with the potential of long-term sound exposure for risk of hearing loss, and it's the basis of most environmental and workplace noise legislation. And for more details on criteria, for buildings, we're running another webinar in a couple of weeks on acoustic criteria for buildings. So one of the topics that I was going to talk about briefly is sound power versus sound pressure. Many of you have maybe heard this, looking at mechanical drawings that have specifications for air handling units, or if you're looking to buy a new dishwasher, you may have seen some of these terms. So sound power level, it's the total rate at which a source emits sound energy into the surrounding environment, so generally the cause of the sound. Sound pressure level represents the magnitude of resulting air pressure fluctuations at some defined point in space, so the effect, so at a distance away from the source. So we have a couple examples here. So sound power versus sound pressure. So we have one, like you take a lamp analogy. So we have the sound power is equivalent to the power of a light bulb. So say a 60-watt light bulb, that's the cause of the light, energy in a room. And the sound pressure would be equivalent to, how bright it is where you're standing. So the effect. And similarly, a heater analogy, we have the power of a heater. So say 1500 watts, that's the cause of the heat or the temperature in a room. And the sound pressure is equivalent to the temperature where you're standing. So the effect, how far away, you are from that. So sound pressure requires a corresponding distance away from, the source, either the light or heat or sound in the case of this topic. So sound pressure level, it depends on the source sound power level. So the cause, the total sound energy, the source receiver distance, how far away are we from the source, reverberation, reflection. So these are, if you're been in a parking garage that's full of concrete surfaces, it can be very echoey. So it's very reverberant and you get lots of reflections, and sound tends to build up in that space. And also the background sound, do you have interference from distant industry? Maybe you're next to the ocean or a lake and there's lots of waves crashing. So you get lots of background sound in that as well. So sound power level, it's a fundamental quantity and it's independent of all of these environmental factors. So when we're doing modeling or specifying a sound level for a piece of equipment in a new facility, we often use sound power because it's the fundamental quantity. It's preferred for specifying the maximum sound output of equipment or comparing two different items. A calculation is needed to determine the sound pressure from sound power or vice versa. And as I mentioned before, it depends on the room you're in, how far away you are, what's the source orientation, if it's a fan and it's directed away from you, all those factors come into play when we're trying to calculate or determine what the sound pressure is. And one example that I like to get into is, my wife and I go buy a new dishwasher or a bathroom fan, and often the ads will say it's 46 dB. Well, that doesn't necessarily tell me, at what distance it was measured or, under what conditions. And so it can be quite difficult to compare it to, compare two dishwashers. So often we have standards that have been developed over time to define how these measurements are done, the distance, the room characteristics, the operational characteristics of the device. And so when you're purchasing these things, it can be important to read the fine print to make sure that you're comparing, like for like items. So how does sound travel in a building? We have airborne sound. So for me talking, that sound is going into my office and impacting the walls and the window of my office, and then through those materials to the other side. One other way is structureborne. So, if I tap my desk, it makes some sound on my desk. So airborne sounds, talking or music, machine noise in a mechanical penthouse or, something like that. Structureborne sound, sound through the structure, vibrational energy through the structure. So footsteps, weight drops, machine vibration when it's connected into the structure. So, for instance, if you're in a concrete condo or an office building, if somebody's drilling into that concrete, that's creating vibration into the structure, and it can travel quite unimpeded through most of the building. Or, for instance, someone walking in the floor above you with hard-soled shoes. So, high heels or cowboy boots, can make quite a bit of structure-borne noise. So I have a little video here just to demonstrate a little bit about structure-borne versus airborne sound. This is just a little music player. So when we touch it to the surface here, it creates the whole surface starts to act as a bit of a speaker. And we put a little piece of rubber between, it actually stops most of that vibrational energy going into that structure. And so when we're specifying, mechanical equipment or other noisy equipment, we'd like to include those sort of isolation parameters in there so that we can stop that transmission of vibration energy into the structure, which then re-radiates as sound in other parts of the building. So how else does sound travel? You know, airborne sound source in a space above, it can travel in a number of different pathways to the space below. You know, direct transmission through our floor, maybe through the floor and then into the walls, or into the walls and down into the walls of the neighboring space and out through that. So example would be like an exterior wall or corridor wall junctions. These are important aspects to pay attention to when you're designing a building. And if you'd like to learn a little bit more about that, we do have another webinar on that in a couple of weeks. Sound propagation, excuse me. So we have our source, and it's generating sound. So it's the sound power level here. You know, it has a quantity of sound energy, and it travels over a path to a receiver. You know, somebody that's hearing it, so a building occupant or an outdoor noise, you know, receptor. And so over that path, there's air absorption. You know, ground absorption is absorbing the sound, as well as the distance that it's traveling. You could have a building in between, you know, so it's got to go up and around the building or around the sides, and all of those come into play when we're, you know, doing modeling or, you know, measurements out in the field. So that's generally it. It's fairly brief and just a quick overview. So we discussed a number of different things. You know, what is sound? It's pressure fluctuations in the air. You know, what is dBA? LEQ or frequency, so different octave bands. You know, what is sound pressure versus sound power? You know, or you know, in sound in buildings, how does it travel from, you know, your neighbor's space to you, or, you know, your office, maybe an enclosed office to your neighbor's office. You know, and just a little bit about us. We're one of North America's largest acoustical consulting engineering firms, founded in 1994. Headquartered in Mississauga, Ontario, which does have fairly regulated requirements for noise. And we have a branch office in Calgary, which I head up. We get it involved in pretty much, excuse me, in aspects of all noise, vibration, and acoustics. So in the built environment, industrial, transportation, defense and security, and even some product research and development. Here's a few photos of some projects that we've worked on over the years. And we get involved in lots of interior buildings, you know, office to office acoustics, keeping separated mechanical units from office tenants or residents. You know, gyms where, you know, they put meeting rooms below floors. You know, for the aquarium, Ripley's Aquarium, you know, making sure that we're not disturbing the fish and other, you know, animals in that space. And thank you for joining us. If anybody has any questions, you know, you can post them on the question board there. Can we have a copy of the presentation? So we're making a recording available, and I believe we are posting it to our website afterwards. And then we have a couple other webinars coming up. The next one is in 2 weeks. It's on reverberation, speech intelligibility, speech privacy. So a lot of interior office acoustics, or you know, churches, you know, community halls, those sorts of things. You can learn a little bit more about that. And again, there'll be about you know, about a half an hour on that, and with some questions at the end. And thank you everyone for joining, and certainly, yeah, tune in and join us in 2 weeks, and there'll be some more. There's some links on our website to that webinar, and I think many of you have signed up for that as well. And we'll stay on here for a little bit in case we need to answer any questions. See, there's a question on COVID-19 here. So We've had the capability of working from home, for quite some time. It did put a pretty drastic change in terms of the office environment. So everybody's been working at home for, I think, close to 8 weeks now. But we've been staying fairly busy. A lot of our projects tend to be, design related, so they're months and months out in terms of project status. So, we've been staying fairly busy with that, which is good. See, there's a comment here about where to find best practices for architecture for interiors. If it's acoustics related, I think, if you wait a couple weeks, 2 weeks, we'll have a webinar on reverberation and speech intelligibility, speech privacy. And then following that, a couple weeks later, we have some more presentations on interior sound criteria for offices or for condominiums. And then also on sound transmission for buildings, either sound or vibration through impact or through airborne sound. Comment here about new building code issues in upcoming sessions. We will be talking about ASTC in one of the presentations. National Building Code in Canada has changed to 47 ASTC. So that's an important change. And we will be talking about that in about 2 weeks. Actually, that one actually will be in 4 weeks, I believe. There's a couple other questions here, interesting ones. Some of them be a little bit challenging to answer in a minute or less, but there's one here: work from home might become a new normal. Do we think it will affect future official, office building noise control practices? I think what we might see, and in fact, we're seeing that with a few new office places now, is flexible office desks. So when you go into the office, you don't have a dedicated closed door office anymore. You have a much like these Regis or WeWork places, you may have a closed door office that you can go to, but it doesn't have your name on the door, or so when you go, you log into your phone and you work from that. And I think acoustics will be a big player in that, because people get used to working from home, where you can generally control the acoustics relatively well. Where an office place, if it's open office, you tend to have some challenges with loud neighbors or phones and concentrating and things like that. Headphones, we see more and more folks in open offices using headphones to try to concentrate a little bit more. Is there a difference between how men and women hear different sounds? Very good question. That's a little bit outside of my realm. Maybe we'll try to tackle that in a different webinar. So what is the reason for the equation of two sounds, 50 plus 50 dB? How do we relate this with reference to building design? Again, that could be a fairly lengthy explanation. I think, what might be good for people to know is that generally a change in sound level of about 3 dB or less is generally just barely perceptible to most people, where a change of 5 dBA is generally definitely noticeable by most people, and an increase of 10 dBA would be considered significant. I have a question here about, are we seeing more acoustic material being more environmentally friendly? Certainly, a lot of the suppliers out there are moving to recycled materials. I know there's a number of them now that use recycled, plastic to make, various sort of suspended acoustical absorbers, wall panels, those type of things. The question here on how to control sound in the existing house, floor to floor and room to room. So we'll get into that a little bit in some of the other webinars that will be coming up. There's one on sound transmission and impact isolation for buildings. So that'll cover a lot of that floor to floor and room to room, sound and isolation and things that you can consider or things that you should consider when designing a building. Question about business in Calgary since oil price drops. It is challenging. There's a lot of government work that's still proceeding, and I think we're going to see that going forward. A lot of the oil and gas sector have cut their budgets to address the situation for now, and we'll see where it goes. Okay, well, thank you everyone for touching base. There was a comment about continuing education credits. So because this is a half an hour presentation, it doesn't qualify, as an official sort of continuing education credit. But however, if you combine all 4 of them, you'll get 2 hours of professional development, which many jurisdictions will allow you to claim or include personal development time, we would be able to or happy to support those where people need it. And thanks again everyone for joining, and we look forward to seeing, or I guess chatting again in 2 weeks. Thank you.